If you've been following the evolution of operating systems and systems programming languages over the past decade, then you already know that Linux and Rust have had an evolving relationship. What's happening now with the Linux kernel and Rust isn't just another incremental update or a minor improvement tucked inside a new version of the kernel. This moment marks a historic shift in how the world's most important open-source operating system will be developed going forward. In late 2025, the maintainers of the Linux kernel announced that Rust, the modern memory-safe systems programming language, is no longer an experimental add-on, test code, or optional curiosity. Instead, Rust has been made a permanent and core part of the Linux kernel's development infrastructure. This decision is the culmination of years of discussion, debates, experimentation, collaboration, conflict, and community evolution. It represents a milestone not just for Linux, but for system software as a whole. But let's take a step back and understand what this means, why it matters, and how we got here. Linux has been the backbone of countless computers, servers, mobile devices, embedded systems, and infrastructure for decades. For most of its history, the kernel, the heart of the operating system, was written in one language, C, with some architecture-specific assembly code where necessary. C has served Linux extremely well, offering low-level control over hardware, performance, and flexibility unmatched by most other languages. But C also carries a cost that long-time developers know too well. It's easy to shoot yourself in the foot with C because it doesn't protect you from certain kinds of bugs, especially those involving memory. Issues like buffer overflows, use-after-free bugs, and other memory safety problems have been persistent sources of vulnerabilities, security holes, and system instability in C programs, including operating system kernels. For decades, Linux developers have battled these issues through discipline, review processes, testing, and tooling. Yet the fundamental truth remained that C simply cannot prevent whole classes of bugs because the language gives the programmer full freedom and full responsibility over memory. It's in this context that the idea of bringing Rust into the Linux kernel first emerged. Rust is a programming language designed by Mozilla engineers and now maintained by the Rust Foundation. Rust's promise, its core philosophy, is to combine performance and control with memory safety and concurrency safety. Rust's ownership model, borrow checker, and type system are specifically engineered to prevent many of the kinds of bugs that plague C code at compile time. That means that a large class of memory errors simply cannot occur in safe Rust code. This attractive combination has driven Rust's rapid adoption in many domains, from web servers to embedded systems to blockchain infrastructure. But integrating Rust into a mammoth, mission-critical project like the Linux kernel is a very different challenge. The effort to bring Rust into Linux began casually around 2020, as part of an initiative called Rust for Linux, led by volunteers and contributors from across the open-source community. The goal was not to rewrite Linux in Rust, that would be impractical and unnecessary, but to allow parts of the kernel, especially new drivers and subsystems, to be written in Rust. Rust could coexist with existing C code and by doing so potentially reduce the number of memory-related bugs and security issues. This project gained approval incrementally, and initial infrastructure support for building Rust code into the kernel was merged into the mainline Linux kernel in version 6.1, released in 2022. That was the first big step. Rust was now officially supported as a language that could be compiled into the kernel alongside C. However, in its early years, Rust support in Linux remained strictly experimental. Experimental in this context meant that Rust was included but not promoted as a core choice. It was quietly available, developers could play with it, and some pieces of code began to appear in Rust, but it wasn't part of the kernel's default developer workflows. Many veteran kernel developers were cautious. Some embraced Rust's promise of safer code. Others worried about the complexity of mixing two languages, the maturity of the Rust toolchain, and the potential for new problems that might arise from this untested experiment. There were spirited debates on mailing lists, forums, and at conferences. At one point, a prominent Rust for Linux maintainer even stepped down, citing frustration with what he called non-technical nonsense, a reference to the social conflicts and debates that can surround large open-source initiatives. These discussions highlighted that technical progress is often as much about people and culture as it is about code. Over the next few years, Rust support matured. Incrementally, more Rust code landed in the kernel tree. Rust drivers for network interfaces, storage devices, and other subsystems were accepted. Tooling improved, abstractions were built, and the infrastructure grew more robust. Developers and distributions began to experiment with enabling Rust by default. Android vendors, for example, started shipping kernels with Rust-based components on millions of devices. These real-world deployments provided important data and confidence that Rust code could operate at the demanding scale and performance required by modern kernels. At the same time, the Linux kernel community continued to refine how Rust and C could interoperate, dealing with challenges such as tooling versioning, build system integration, and cross-compilation support. Then, in late 2025, something changed. During the Linux Kernel Maintainers Summit, a gathering of core developers and project leaders, the community evaluated the progress of Rust support. After extensive discussion, it was concluded that Rust had proven itself technically, procedurally, and socially. The experimental label that had accompanied Rust support for years was officially removed. Rust was declared a permanent part of the kernel development ecosystem. This isn't merely symbolic. It formalizes Rust as a core language in the kernel project, alongside C and assembly. In practical terms, it signals to developers, corporations, distributions, and the broader open-source community that Rust isn't a temporary experiment or side project. Rust is now part of the kernel's future. Why does this matter? And why is it being described as historic? To understand that, we need to appreciate what Rust brings to the table and what its permanence implies for future development. Memory safety has been a chronic challenge in kernel development. Kernel bugs involving memory can have severe consequences because they run with the highest privileges on a system. A single mistake can crash an entire system or open the door to privilege escalation exploits. Rust's ownership model, enforced at compile time, prevents entire categories of memory errors from ever compiling, meaning that many bugs simply cannot occur in safe Rust code. This is not to say Rust eliminates all bugs or all vulnerabilities. It cannot help with logic errors, race conditions, or misconfigured systems. In fact, Rust code in the Linux kernel did eventually receive its first assigned CVEA race condition in a Rust implementation of the Android binder driver, illustrating that no language is a panacea. But even in that case, the type of vulnerability was significantly different in nature from typical C bugs, and the existence of the Rust code highlighted how safety properties changed the landscape of potential flaws. Rust's permanence also has implications for the culture and skills of the kernel development community. For decades, C has been the lingua franca. Most kernel developers are deeply experienced in C, understand its patterns, and accept its pitfalls. Introducing a new language required not just technical tools but also training, new review practices, evolving documentation standards, and community support. With Rust now established, future kernel contributors will increasingly need to learn Rust, or at least work in a mixed codebase where Rust and C coexist. This is a generational shift in skills and expectations. For some developers, this is a welcome modernization. For others, it represents a challenge. But regardless of personal preference, the permanence of Rust is now a fact, and it will shape how future kernel subsystems are written, reviewed, and maintained. Another dimension to consider is the broader ecosystem. Linux is not just a single piece of software. It is the core of an enormous ecosystem ranging from cloud infrastructure and supercomputers to smartphones and embedded IoT devices. The choice of languages used within kernel development influences not just security and stability, but also the developer tooling, compiler ecosystems, education pathways, and long-term maintainability of that ecosystem. Rust's adoption in Linux sends a powerful signal to companies, educational institutions, and open-source projects that memory safety and modern language features are priorities for systems programming going forward. It may inspire other operating system projects to follow suit, further entrenching Rust in the world of low-level software. The decision to make Rust permanent also reflects a careful balance between innovation and continuity. Even with Rust in the kernel, C will remain essential. Most of the existing kernel is written in C, and there is no intention to rewrite it wholesale. Rust is primarily a tool for new code and new drivers, especially where safety guarantees provide clear value. Rust will interoperate with existing C through carefully designed bindings and infrastructure that ensure the two languages can coexist without compromising performance or compatibility. So while Rust gains permanence, it does not displace C, it augments it. Developers will need to understand both, and kernel contributors will need to navigate a multi-language codebase where the strengths of each language are used in appropriate areas. From a historical perspective, this moment is remarkable because it represents one of the most significant shifts in kernel development practices in decades. Linux has weathered many transformations over its long life: new file systems, virtualization technologies, security frameworks, and hardware architectures. Yet for all that change, the core language and methodology remained stable. Bringing a new language into the kernel and elevating it to permanent status is comparable to milestones like the adoption of modular kernel design or the introduction of widespread threading and preemption support. It's a foundational change in how work gets done. Looking ahead, the permanence of Rust will influence the kinds of innovations we see in kernel components. Rust's features: memory safety, strong type systems, modern concurrency primitives, and expressive abstractions will make it attractive for developers working on drivers, memory allocators, security modules, and experimental subsystems. Over time, we may see entire families of kernel extensions that were previously too dangerous or error-prone in C become viable targets for Rust implementation. Security-critical code, in particular, is likely to benefit from Rust's guarantees. As distributions and maintainers become more comfortable with Rust, it's possible that Rust will be enabled by default in many kernels, further smoothing the path for new Rust code contributions. Of course, challenges remain. Not all architectures supported by Linux currently have full Rust support. The Rust toolchain itself evolves rapidly, which can complicate kernel build systems that need stability and reproducibility. Interoperability between Rust and C still requires careful attention to ensure data structures, calling conventions, and memory models align correctly. And as the CVE in a Rust driver underscores, Rust does not automatically eliminate bugs, it changes their nature and distribution. Developers still need to write robust code, understand concurrency and logical correctness, and engage in rigorous review and testing. Yet for all these challenges, the permanence of Rust in the Linux kernel represents a vote of confidence from the most demanding community in systems software. It says that Rust's promises have been validated at scale, that developers and maintainers across the ecosystem see value in this new direction, and that the future of kernel development includes safety as a first-class concern. For students, programmers, and engineers watching this unfold, it's a reminder that the field of systems programming remains vibrant and evolving. Languages and tools change over time, but the core challenges of building reliable, secure, performant software at the foundation of modern computing persist. The Linux kernel's embrace of Rust is a step toward addressing those challenges in a way that respects the past while building for the future. And so as we reflect on what it means when we say, Linux just made Rust permanent, we can see why so many are calling this a historic moment. It's not merely the addition of another language. It's the opening of a new chapter in the story of how the software that powers billions of devices will be written, maintained, and secured for years to come. It's a testament to the power of open-source collaboration, the resilience of a community willing to evolve, and the enduring quest to build better, safer technology. Rust in the Linux kernel is here to stay, and its impact will be felt for many cycles of innovation yet to come.